Okay. Hi, everybody. We continue our work. Today, I am going to illustrate for you another 3 interesting examples related to logistic regression. Each of the examples will serve a number of targets and will cover different interesting topics related to the techniques used for logistic regression tasks. We begin with the first example. The most interesting thing in this example that we shall create our own logistic regression dataset. The dataset will not be imported from any other library or repository. You can do it yourself and you will see how we do it. Then we shall apply the STATSMODELS library to define the model and to carry out necessary predictions on the whole data set. And at the end, we shall estimate the quality of the logistic regression by using the score function or the confusion matrix. So at the beginning, we import the required libraries, as you heard now. So we need to import the STATSMODELS with the interface API as SM. And we shall use SKLEARN library in order to divide the data to, or split the data to training and testing parts if necessary. And at the end, we shall also carry out an evaluation to the quality of regression by using the accuracy score or the confusion matrix or both. So at first, we create our data set. To guarantee repeatability when working with the random generator, we use a seed. The seed which we use always is 42. Number of samples are selected to be 90. It could be any number, of course. At first here, we create an array using the random generator with a number of samples equal 90, as it is shown here. The array is two-dimensional, so we are working with 2 features only. And the created numbers are multiplied by 7 just to raise up the level of values. So here we have a two-dimensional array representing 2 features of the data set. This is the independent 2 variables, x1 and x2. Now we need to create the target column which represents the dependent variable. And this, for logistic regression, it should be categorical values as 1 and 0. So y is created to be as selected all rows with the first variable, which is x1 here, x of all rows, and the 0 indexed column, which is representing x1, plus another component, all the rows selected with the first index column. This is the 0, this is the first index. Now we have two components of values. We add them together and state that if it is the sum is more than 5, for example, we use as type function so that the output will be integer 1, or if it is less than 5, the output will be 0. So using this format, we guarantee that we have now a dependent variable with values 1 and 0. By this, we have already a data set ready. Now, the features here, we want to make them, to convert them to a data frame. And the y also dependent variable, we need to convert it to a series. So we use pandas data frame. We pass there the values x, which already computed, and the names of the columns, which are assigned as feature 1 and feature 2. So feature 1 and feature 2 are the names of the two columns which are created, and the values associated with each of them are given as x of 0 and x of 1. So now we have the data frame of the features ready. We do the same with the dependent variable, but because it is only 1, here we do not need a data frame, we need only a series. So PD dot series, this is a function series, and we pass there the same thing, the values of y, which were created just now, and we give this dependent variable a name called target. So now we have also a data series ready. If we want to have a look, we can print xdf and ydf. I have printed the first 4 indexes or 5 values from 0 to 4, from 0 to 4 for both of them. You can have a look here. This is x, which is created as an array, 2-dimensional array. This is the first column, and this is the second column. Now this is normally an NumPy array. It is converted to a data frame. Here we have indexes from 0 to the 90, 89, and the features names, feature 1 and feature 2. So this is the data frame of the features. And this is the column or the series which represents the values, the discrete or categorical values, 1s and 0s, which represent the target. And this is the index values, 0, 1, 2, 3, 4, up to 89. So now we have both of them. Having both of them with us, now we can initiate our logistic regression function. When working with the STATSMODELS, remember, we work with a function called logit. This is one thing. The other thing to remember is when we work with the interface API, we need always to add a constant before we do anything with the stats models. So at first, from the stats models, we call and constant function, add constant function, and pass there the values of the X array, XDF, which is the data frame XDF. Here now, we shall have a new data frame with 3 columns. The second and third column are those which we have seen just now, and the first column will be a column of ones. This new data frame, we gave it a name XDF X underscore DF underscore constant to remember that we have added a constant. So now this is the data frame which we will work with. Okay, if you want to have a look, I have printed it for you. I have printed the head for you, so you can have a look and see that really it has 3 columns, as you see. The second and the third column are those which we have seen in the XDF, and the first column, which is with one's values representing the add constant. And again, I remind you with this that this is necessary to do always when working with STATSMODELS interface API, so that the algorithm will take care and find for you the intercept value. If you work with the function API, which is imported as SMF, here you do not need, in this case, to add constant. But I am adding a constant just to remind you. So, okay, now we have prepared the data frames in the required form. And now we shall call the logistic regression function of STATSMODELS. Logit, from SM we call logit. This is the brackets which refer to that we are calling it. Now in this action we are initializing the logit function, and here we have to pass 2 values, one of them YDF and the other one X underscore DF underscore constant. Remember that the first added data here is the dependent variable, the target, and the second one, which is the features. This is required by the dataset of STATSMODELS. You cannot add at first XDF constant and then you add YDF. This is forbidden for STATSMODELS, and you must begin with the target series column, and then you add the features data frame 2 columns here, 3 columns. This is an important. If you remember how we do that in SKLEARN, we at first have to pass the features, the independent variables, and then we add the dependent variables. But that is only in SKLEARN. In STATSMODELS, again, we begin with the dependent variable column, and then we pass the independent data frame. Important also to tell you an important issue here. When you initialize the STATSMODEL logit function, okay, you have done it as you see, and you passed these values here at the initialization stage. But if you work with the SKLEARN and remember what we have done before, you will find that there we only used two brackets and they are empty. And there we need to pass these values for fitting or for learning the dataset, but not for initialization. Now, at STATSMODELS, again, the action is different. Now we have initialized the model, we called it logit model. Now we want to apply it to the dataset, to read it, to learn about it, or to fit it. Now when we call the function logit model dot fit, the fit function is empty. We do not pass anything here. This is in STATSMODELS only. But if you work with SKLEARN and you call the initialized model, you have to pass here the independent variables at first and then the dependent column or the target column. So please take care of these differences. They are very important and specific for every library of these two very famous and very important libraries. Anyhow, now we have already initiated this model. We apply it to learn the dataset, but we do not apply anything here, as you see, because we already used it at the stage of initialization. And we now, after learning the dataset, the model is ready to give results and to carry out predictions. So we assign this result as a result here, and we ask the result to give us a summary of what has been done. If we print this summary, result.summary, usually you will have the table, the famous table of STATSMODELS. And for this specific example here, we have the value of the intercept. This is the value of the intercept. It is always the first one. It is called constant. And feature one is given its slope here, the slope. And this is the coefficient, the other coefficient, which is the slope of the second column. Reminding you with the basics here, the dependent variable has a name called target. We gave it a name target. The model which was used logit, its name is logit. The optimization method which was used internally by the algorithm in order to optimize the coefficients is called MLE, maximum likelihood estimation. Now here you see also an information telling you how the work was done and the quality of logistic regression. It is really very high and very acceptable. Okay, now what else? We need to make some predictions here and to evaluate the accuracy of predictions. We already know the accuracy, but let us try to have it again. Also, one interesting thing here I want to note about it. At first, as you see, we need to make predictions. So we ask from the result, predict the values which you are interested with. Here, I have selected all the values of the data frame. XDF constant. I did not split the data to a portion for training and a portion for prediction because all the data was taken for training. Okay, so I will get the values of probabilities, and these probabilities now will be fractions from 1, fractions of 1. If you have a look at the head of the probabilities, you will find them also downwards. Here they are. This is the first 5 values, and as you see, they are all fractions of 1. These are the predicted probabilities. This is the first 5 only. We have already now made predictions, as you see, but we are always interested to convert the predicted values, these fractions, to either 1 or 0. So in STATSMODELS, we need to include a logical statement here, which includes a conditional case with a given threshold value. So probabilities, if they are more than half, dot as type integer, give us an output integer as 1 if it is more than 0.5. If it is less than 0.5, then the output will be integer 0. This is also required by STATSMODELS, and you have to write it always. With SKLEARN, you do not need to do this. This is done automatically and internally. But now, after writing this statement here, and we have got the predictions, if you look at the predictions, they will be now rounded to 1 and 0, which is required. So here the predicted classes, the first values, these first values now, are converted to 1, 1, 0, 1, 1. As you see, 1 here is considered as 1, 1 is considered as 1. This is, of course, very small value, it's about 0. This is again 1, and this is again 1. Here they are. So the work now is done, and what do we need is to evaluate the accuracy. We call the accuracy score. It was imported at the beginning here. Accuracy score, and also I have imported confusion matrix. Both of them are imported, so I want to use them both to compare between the results. So model accuracy, as you see here, accuracy score, I pass there the 2 values, the real values of the dependent variable YDF, and the predicted values, which are predicted for the independent variables. Now, this function will give us an accuracy value, and it must be very high. As we have seen there, it was 0.9. Here it is approximated to 1. It is exactly 1. So this one means that all the values which are predicted by the log fit function is accurate. To be sure, I have called the confusion matrix and passed there the 2 variables again, the true and the predicted values. I have got the answer here in this location called the confusion matrix. When I printed the confusion matrix, I shall have this matrix 28, 62, 0, 0. As you see, 0, 0 means the 0, 0, there is no faulty predicted values at all. All the predicted values which are in this diagonal, which represent the accurate predictions. And because these are 0, 0, so if you add this 28 to 62, this will give you 90, which is the total number of the samples which we have at the same beginning, which means that all the values which were predicted are accurate. Okay, so now we have finished with this example. I have reminded you with some basic things, with some comparison between the action of STATSMODELS and SKLEARN, and how we created the dataset with its two parts, the NumPy two-dimensional array at the beginning, which represents the independent variable values, and the other column, which represents the dependent variable, and how both of them were converted to data frames and used in the regression process. So this example, I think it is now clear, and you have learned, or you have deepened your knowledge, and now solidly you know how to work with it. Okay, we have now another example here. In this example, we shall use exactly the same dataset which we have created in the previous example. So as you guess, the target now is different. In this example, I am going to plot the scatter plot of on the plane of the two features, feature 1 and feature 2. I shall have a plot there, and I shall overlay on this plot the decision boundary, which is a line. But here, I am not going to use only the mesh grid approach and then to find the predicted values as the Z values or the height values. I am going to use it and to use another new approach by using a specific function for logistic regression called decision boundary display. Decision boundary display, which is a function of SKLEARN. So in order to work with it, I have to import it. So let us go and see what we are going to do. As we are going to work with SKLEARN, you can guess that we are going to split the data into a training portion or part and a testing part. So we import train test split function. We are going to work with logistic regression because we are working with SKLEARN, so imported logistic regression. We are going to evaluate the accuracy, so we import accuracy score, confusion matrix, and if you need also, there is a third way to do that, which is the classification report. All these are now clear for you and why it is imported. We are going to plot by using the decision boundary and scatter plots, so we need to use matplotlib library, and it is imported as PLT. We also going to use Seaborn library, and it is imported as SNS, and it will be used for plotting also, because Seaborn is really sometimes more easier to work with than matplotlib, though it is built on the basis of matplotlib and Python. But don't forget, we are going also to import the decision boundary display function so that we can plot directly the decision boundary between the two predicted classes. Okay. Now we create the data set. This is a repetition of what we have done in the previous example, so I will not go through it. I go directly and initialize the logistic regression algorithm. So I call the logistic regression function. These are the two columns. I did not pass here any data values as we did with the stats models. It is empty. Only I have passed here random state 42 so that we can get repeatable values, not more. So now the algorithm or the model is created and it is given a name model. Normally, this is common in working with regressors. Now, having the model, we need to fit it to the dataset. But remember, now we have to pass the dataset for the SKLEARN. In the stats model, we did not pass anything here. Here we pass the X-train. We have selected the X-train portion for training and Y-train. And of course, as a result, we can find the coefficients which were founded by the stats models there. Here, these coefficients. Let us see what we shall have here. I think I have printed it. Let us see, gentlemen. Here we created it. Yes, here is the function. Here the model coefficients. This underscore here tells you that these are the coefficients which are predicted. The underscore shows that these are predicted values. It is called model coefficients. If we have a look here at the model coefficients, here they are. This is one of them, and this is the other of them. We have two values. Okay. Now we have made prediction. We have just learned the data set, found the coefficients, and now we want to carry out some predictions on the X-test value. We have divided the data to X-train and X-test. We shall use X-test now because now the algorithm did not know anything about its structure. This is a way to check about the performance of the predictor. So model.predict X-test will give us predicted value. And if we want to predict the probability, okay, we can do that by calling predict underscore probability function and pass there also the same value X-test. So now we have two pieces of information. One of them, the predicted values as discrete values, 1 and 0, and the other one as probabilities. Did I print it? Yes, I have printed them. I have printed the Y predict. Yes. And Y predict probabilities. Both of them exist. So have a look here. Y predict and Y predict probabilities. So this is the Y predicted 0, 1, 0, 1, and these are where is the Y predicted probabilities. Here it is. Predictions made on the test set. The actual values 0, 1, 1, 0, 1, 1, these are the predicted values, and they are exactly as those here. And the predicted probabilities are these values here. They are presented as fractions of 1 as usual. Okay. What do we need else? We may need to evaluate the work and the accuracy of the logistic regressor. For this, we use accuracy score, we use the confusion matrix, and the classification report. All of them require the same parameters, Y test and Y predicted, Y test and Y predicted. So you can also have a look here about the accuracies which we achieved. The model accuracy is 1, exactly as what we have received from the stats models. The confusion matrix now gives us 0 values here in the off diagonal, which means there is no values predicted falsely. All the predictions are correct, and there are 5 of the first feature and 13 of the second feature, and the total is 18. Why it is 18 and not 90? Because we have predicted only the test values, not all the values, and the test values are 20% of the whole set. 20% of 90 is 18, so we have only predicted the values of 18 numbers. So 5 of them are belonging to the first class and 13 of them belong to the second class. If you want to in advance to know how this happens, here they are. When I plotted the plane of the features, this is feature 1, the axis, the other axis, the ordinate is y. Here in this, the decision layer or the line which divides the 2 classes, here you find 1, 2, 3, 4, 5. This represents 1 class, and the other values which represent the second class. So everything is normal and okay. Okay, now let us go up and see the new thing here, which we did not see before. So how to plot the scatter plot of the data set. Remember, we shall use the values of the X feature values, feature 1 and feature 2, and here they are. But as you see here, X and here is Y. X is equal X test for all the values, and 0 represents the index of the first column, and here also for all the row values, and this is the index of the first column. Exactly as we did with matplotlib, nothing different. And then we have define the maximum and minimum value of the first feature and the second feature. We have given margins -1, -1, +1, +1, and then we use the NPy linspace in order to find the values of the X parallel lines and Y parallel lines, which are the mesh grid lines, XX and YY. And then we have predicted the Z value, and then we converted the Z value again to a 2-dimensional. All these things we have done in the previous lecture in order to plot the decision layer or decision line in this case, which is shown here. You know this, I have explained this in detail in the previous lecture. The new thing here and interesting thing I wanted to show you, which is new, is really how to use the decision boundary display in order to make the same plot without working with mesh grid, without evaluating the mesh grid points for prediction. So as you see, we call the decision boundary display from estimator and open brackets to pass the required parameters. These parameters are usually decided by the syntax of this function. Of course, you can refer to the SKLEARN, and there you will find a lot of information about it, but as you see, it doesn't require that much. It requires to give the name of the model. It is called a model. The features X, AX, this is the coordinate. Response method, predict probability. Plot method, contour. And they are generally repeated always. The levels here, remember this level which we have talked about in the previous lecture. This is the threshold value which divides the two classes from each other. Length style, the line style is dashed to be dashed, and the color to be K, which is about black, like black color. And that's it. With this information now, if you print plot PLT show, you will get this figure. These are the dashes which represent the boundary between the class 1 and class 0. You will have the same results, 5 values here and 13 values here. 5 values here, sorry, 5 values here and 13 values here. It is exactly the same result. So as you see here now, we have learned also an interesting new thing, which is how to use the decision boundary display function. If you need to know more information about it, no problem. You can go to a SKLEARN and find it there. You go to the help here, and from the help you can go directly to SKLEARN. And for the sake of comparison, we have compared both methods, and we find them, as you see, exactly the same. They gave the same results. Here they are, the same results. And also I have especially used the same data set which we used in the previous lecture, so that to compare between the performance of the SKLEARN and the performance of the STATSMODELS. And as you see, the accuracy was about 1 in this case and in the previous case. The only different thing between them, as you see, is here we have made predictions on 18 values. There we have made predictions for the 90 values only, all together. Okay, now what is there here? Now this example, which is solved by using SKLEARN, I have solved it for you only by using LabVIEW, and specifically by using LabVIEW-PLAIY library. And because I am going to work with the same data here, so the same data must be used with the PLAIY. So what I have done here, the data which represents the X train and Y train and X test and Y test, I have saved them here, as you see, X train, Y train, X test, Y test. I have saved them as CSV files. They are given new names, and they now are saved in the Python, this Python directory. Now, when I go to LabVIEW, I shall read these 4 CSV files and make use of this information in PLAIY dataset of LabVIEW in order to also classify the X-test values and find the predicted values, and at the end compare the values which I receive with play with those which we have received just now, which were 5 and 13, if you remember. Okay, so now I will finish with the Python and move to the LabVIEW to show you the same work which is done differently. As I told you before, the Play library works only with LabVIEW, which has 64 bits. This is LabVIEW version 25. I am opening this version now, and I shall ask to open the required file here. The file which I am going to open, I know it because I have made it so that to be demonstrated by you. It is called, I think it is this one, third logistic regression by using play. So I double click it. Now it will open. Here is the front panel in LabVIEW. If I go to the block diagram, let me explode it for you. Now here it is. The program, as you see, begins with these 4 blocks. This is a function of LabVIEW which reads CSV files. And in order to read the CSV files, you just refer to the path of the file where you have the CSV files. Here I have these 4 files which I have just saved in Python. This is one of them, this is the second, this is the third, and this is the fourth. This is X-train data, this is Y-train data, this is X-test data, and this is Y-test data. If you go to the front panel here, you will see them clearly. Here, the first, this is the path to Python. This is the name of X-train, which is, it is saved in the Python directory, and this is the whole path, beginning from the hard disk C up to the name of the file. This is the other file which I have saved, the Y training, and this is the X testing, and this is the Y testing. So these addresses or names are now known to the functions here. They are known, and this function now will give data, the output, and this output, it gives 2-dimensional data, 2-dimensional, and this, all of them give 2-dimensional, because this function read spreadsheet files with delimiters, comma, gives to, as you see, dimensional arrays. If you want to have a look at them, they are also shown here. This is one of them. This is the second. This is the third. This is the fourth. This is the X training. This is the X testing. This is the Y training. This is the Y testing. Both of them are 2-dimensional. Look, this is 2-dimensional array, 2-dimensional array, 2-dimensional array, 2-dimensional array. So everything is as should be. But for the work with LabVIEW, of course, I need to have a linear classifier or linear regression method. Here it is. If you go to the TDF, Technology de France, and to the play here, and then you go to not data processing, to regression, machine learning here. And now I'm going to go to, no, again back to machine learning, to supervised machine learning. Now in supervised machine learning, I want to go to classification. Here is a classification. In this classification, one of these is the Gaussian process, no linear classifier. If you plot it here, you will see it is this one here, logistic regression. Under logistic regression, you can also have choice to select different algorithms. I did not select anyone except the default value logistic regression. But this is not required by me. I keep it away. Now also, now I have this regressor. Instead of working with SKLEARN, now I shall work with the linear classification VI. This exactly an SKLEARN function, but it is transformed by the TDF to a palette-like structure. If you want to know about it, you do not know how to work with it, you just right-click it, go to the help, and now you will have a page logistic regression. And this logistic regression is for SKLEARN, scikit-learn. So all the information here, which is related to how this regressor works, exactly it works as with the SKLEARN. Here, as you see, it is with the, for example, LT penalty term. Remember, we have already know about it. So what applies to this palette also applies to the initialize or applies to the set parameters or fitting. This is fitting, for example. Click on it and go again. It will open to fit XY sample weight equal none, and you have to pass there the X. You remember, the first you have to pass X in SKLEARN, and secondly you have to pass Y. And what is X and what is Y and all the information about it, you can have it here. So now what I have done, I have taken the two-dimensional arrays, X-train, I have fed it to a property node which supplies the data to the regressor, and the Y value, it is also two-dimensional, but here it is required as one-dimensional. So I have here converted the two-dimensional to one-dimensional. This is maybe known to you. You have indexing by indexing the columns. We have two columns there. I have taken the first column of interest and fed it here. And now the data is fed to the classifier. The other, for predicting, I want to work with the X-test, which is also, this is the X-test, which is also a two-dimensional. So I pass it to the other property node for fitting, for prediction and fitting. And also the Y-test is also taken and converted by indexing to a one-dimensional array here. This is all what I have done. Now at the output, I here get the, as you see, the predicted values. Here, this is an array, two-dimensional array, which includes the values of predicted values, which is zeros and ones. Here it is called C here. If I double click it, here it is. You shall see that the output here is 0, 1, 1, 0, 1, 0, 1, 1. Now, we have only ones and zeros. So how many are there? 0, 1, 2, 3, 4, 5. Remember, what we have got in SKLEARN and in STATSMODELS, only 5 values predicted as zeros and 13 values predicted as ones. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. So exactly the same. At all, no difference. But one thing here may arise. Suppose that we are predicting a high number. Suppose this C two-dimensional array includes 200 or 500 elements. And these 500 elements are divided to zeros and ones, and I want to know the total of zeros and the total of ones. To count by eye, it is difficult and it is not practical. What I have done to do that, I will show you what I have done. I have done it here by 2 ways. One way, I have included this piece of code, and the input to this piece of code is this array, this two-dimensional array here. It is fed, as you see, it is first indexed, and then it is fed to this for loop. Inside the for loop, I don't use any function except the search one-dimensional array. Search one-dimensional array is, here it is. If I go to the arrays, here it is, threshold, sorry, this one, split, here, search one-dimensional array. This function is used in this loop only, and the other are just for data manipulation. The output here, I get 2 outputs. One output shows you what are the types of values you are having within this array. The answer will be, I will have 0 and 1. These are all the types which we have. And the count here, against the ones you will have a number, and against the ones you will have a number, and these numbers will be 13 and 5. If I go to the front panel, let me click it to be sure. Here it is. Now, if I go to the front panel here, I can see these 2 outputs. The elements found ones and zeros only. The ones are 13 points and the zeros are 5 points. The importance of this work here is not just to show you that, but the importance is if you have this one and zeros, very high number of 200 or 400, and you want to divide them, you can do that only as I did through programming or by plotting. Today I'm showing you it through programming. In the next lecture, I will show you how you can see it by plotting. But even by plotting, you have to count it again by plot point by point. So this is, I think, the most interesting thing to do in LabVIEW is to extract exactly the number of ones and the number of zeros. Okay, another thing I have done here for you really is I have also taken the cluster of the predictions. Here is the predicted values. This is the cluster. I have here a prediction probabilities VI. This VI is included within the TDF. Here, TDF, play. Here, if you go here, you will find this is data processing. Maybe somewhere here I have no. Here it is. Here it is. So I have used again. Is there any information about it? Yes. If you do not know, you go to the help, and also you will know some information about the predict probability function. And this function, which is here, is exactly this one. It is only converted to a LabVIEW format to be used directly by LabVIEW. But in essence, it is a SKLEARN function. I have taken the output from it here. It is a 2D. I have found its size. Here it is 18 points, two-dimensional. The array is two-dimensional there, and 18 points. Here it is two-dimensional, 2 lines, as you see. I have indexed it to one-dimensional, and now I have also created from the, I have done as we do in Python. I have used the threshold 0.5. If the input is less than 0.5, you will get 0. If it is more than 0.5, you will get 1. So at the output here, I shall have an array with ones and zeros. Again, if I double click it, 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. It should be more than that then. Well, it is 7. It should be 13. 1, 2, 3, 4, 5, 6, 7. Is there something wrong? I am not sure. But the array here must contain the values of zeros and ones, and they must be equal to, here, let me put 18 instead of 30. And then, now let me run the program again. This is still running, yes? Yes, sure. It is, yes. Now it is okay. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. That's it. 1, 2, 3, 4, 5. There are 5. Exactly as I have got here, I have got here. So, but of course, this is much interesting and more perfect to work with. Concerning the accuracy and the quality of the work of this regressor, as you see here, the score is equal to 1. Where I have got the score from, if I go there to the front panel, here it is the score, the output. Here is the output score. I double click it, I'll see it is 1. So the score is 1, exactly as the score which we have got with SKLEARN, exactly as that which we have got with the STATSMODELS, the same numbers of predictions without any difficulty, without any errors. So, excuse me, I think that the work is done. It is done according to me. It is done perfectly. There is no difference. And my advice to you is to read this lecture once or twice. If you have questions, you can ask me, but this is perfectly working. And according to me, this is in a better fashion even than SKLEARN itself. Okay, so with this, I finish this lecture. I hope that this was of interest for you also. See you in the coming lecture, and goodbye.